Hello, everyone. Welcome to the robotics final project presentations again. We have our fourth session today and the final session. And we got 4 exciting presentations to wrap up all these presentations. Again, just a few reminders before we start for the students who are presenting. Make sure to introduce yourself first before sharing your presentation, followed by sharing your presentation, unmuting your mic, and then showing the video and the presentation. You got 15 minutes to do it, and then we'll take 5 minutes for question answers from everyone. So before we begin, we have guests again, and how about the guests? If you want to introduce yourself, just say your name and where you're from and a title. That would be great. Please go ahead.
Hi, my name is Yanni Zhou. I'm from General Motors. I have automation standard and the smart factory. So I'm excited to see the project come from you guys. A lot of innovation for sure.
Welcome back, Yanli. Good to see you again. Go ahead.
I'm John Tusky. I'm president of College for Creative Studies, and I'm excited to see these presentations, and I'm excited about our collaboration with the Augmented Reality Center that you guys are starting. So it's I'm really looking forward to this. Thank you for inviting me.
Thank you, Don. We're glad to see you here, and hopefully you'll see some of our robotics side of the engineering students. Anybody else here?
I'm Michael Breen. I'm the Sales Application Engineering Manager for KUKA Robotics, and I'm looking forward to all the prezos.
Welcome, Mike. And I think that one of the presentation has a KUKA Titan robot in it.
That works for me.
Okay, anybody else? Anybody else here?
I think Sam is trying to talk. We can't hear you, Sam.
I see him now. Go ahead, Sam.
Yeah, my name is Sam Angeluni. I'm a creative director and president of the Alumni Council at the College for Creative Studies and a founding member of the ARC team. And this is my third watching these presentations and looking forward to it.
Welcome back, Sam. Good to have you here. And we have Kelly also joining.
Yep. Yes, I'm here. Hey, everybody. I'm excited to see the rest of the presentations. Everybody has just done a great job. I'm with SECS Career Services. And just a friendly reminder, I know you've been busy getting ready for all of these, but don't forget that we are looking to get your project posters sent over to us by the 21st. So I guess that's a week from today. And so both Laura and myself emailed you. So go back to your email. Don't send them all to me. Half are going to Laura, half are going to me. So check your emails again, and we'll be posting your projects out in LinkedIn next week for a virtual expo.
Thank you, Kelly. So that's an important, after this presentation, the next thing is the virtual expo. And we will have all the demo videos linked up to that page along with your posters. So it'll be a great way to share it with the rest of the students and whoever missed these presentations. Anyway, so with that, let's start with our first presentation for today. Group number 16 is doing robotic optic polishing. Interesting application. So please take it away, group 16.
Hi, I'm Brian Clarkson.
Hi, I'm Ryan Allen.
Hi, I'm Hussein Bazi.
And I'm Kevin Bobernick.
Let me go ahead and share my screen here. Looks like that's coming through. So let's get started here.
Yes. So in this presentation, we will give you a quick introduction and overview on our project. Then we will discuss geometry compensation, raster two-pass generation, simulation rendering, and we will end the presentation with some of the challenges that we were able to overcome. and some potential improvements, and we will cover some of the other application for our project. So robot polishing is a great method to improve safety and consistency of the polished product. These products, in some cases, would require extremely precise robotic design. And a good example of this product would be the ellipse mirror that we are polishing in our project. So what's interesting is that we can leverage our electrical engineering background to root cause issues and root cause some of the quality problems. Specifically, we can leverage our signal analysis skills. And here we gave some examples on how we can use power spectral density, Fourier deconvolution, and filtering to determine our polishing strategy and root cause some of the problems we face during the design phase.
So here's an example of a commercially available robotic polishing system. It has 3 prismatic axes and 2 revolute axes, and a workpiece mounted on the final Z stage, and a rotating tool spindle for applying the polishing force. This tool spindle features a load cell for being able to constantly monitor your polishing force, as well as being used for geometric probing on the machine to determine the orientation of the optic which you're trying to polish. So before proceeding further, we'll hop over to our demo video. And currently we see the tool being pressed against different parts on the optic. While we're doing this, we're measuring the load cell force, and we can use that to determine if there's any tip tilt of the optic as it's mounted in the machine. After performing our geometry probing, then we proceed with the raster toolpath, which will later show some of our MATLAB methods for automatically calculating a total of 6,000 points on a raster toolpath for this curved optic. It's hard to see from that angle, so we were gonna give a little bit more visibility. Here we are actually looking behind the mirror and are looking at the superimposed raster path along with the rotating polishing tool as it is moving along the optic. Starting from the beginning of the raster path. In this view, we have better visibility of the B-axis of the machine upon which the rotating tool spindle is mounted. Here we can see that all axes having to operate simultaneously and in unison to accurately touch all points on the mirror. Similarly, another view from the top. And we'll speed things up here in a second. Currently, we show the optic as being mounted to the machine using a vacuum chuck. However, a problem could arise. We don't want that to happen, so we'll discuss other mounting options. So back to our presentation. So in looking at this machine, we see that we have 3 prismatic axes and 2 revolute axes. Using standard Devenant-Hardenberg parameters based on the joint offsets between these joints, we are then able to derive the Devenant-Hardenberg standard parameters, which then yield a series of transformation matrices which relate the different coordinate frames on the machine. We then relate that to the normal vector that the tool is oriented for a given position. We then use that orientation and derive obtain the positions of both our A and our B axis in order to meet the orientation required at each point on that curved surface of an optic. So the optic we chose to polish in this case is a fairly generic ellipsoidal mirror. And the benefit of ellipsoidal optics is that they take the light coming off of a focus and refocus it elsewhere. Largely beneficial in places where you need to have a focus distribution from point sources of light. And then from that optic prescription, then we can figure out, based not on the position of the mirror in the ellipse coordinate system, we look at it in terms of the substrate coordinate system with respect to the mirror itself and its center. In doing so, then we can easily derive the horizontal and vertical positions of both the source and focus. And given the property of an ellipse that all points on an ellipse are are the sum total between the source, the mirror, and the focus is equal for all points on an ellipse. So for a given XY position on the mirror, then we can calculate the height of the mirror in its own substrate coordinate system for the mirror without having to perform additional rotation matrices for transforming between the ellipse coordinate system and the mirror coordinate system. Then once we have the X, Y, and Z of the source, the mirror point, and the focus, then we can draw 2 vectors between the source, the mirror, and the focus. By taking the angular bisector of those rays, then we derive the surface normal vector, which is then the orientation that we require for the machine as we're polishing over that point. And then Kevin was going to discuss how we can figure out where it is in the machine.
All right, so I'm going to be discussing geometric compensation, which is just a fancy way of saying it's our process to minimize as much error as possible while we're polishing the surface of our lens. The errors can be given by flatness, parallelism, system errors of the grinding, polishing fixtures. A lot of these geometric errors are present when you're loading optics into a machine. And geometric compensation is just our way to obtain a uniformity in polishing force across the entire tool path. Here, our first process when we're doing geometric compensation is we do edge finding. Edge finding is our way to find our X, Y, and our roll values. We, from the picture on the side is just our picture of the lens and some coordinates. We take those, we'll throw them in our formulas with the transformation matrix, and we'll get our X, Y, and our roll values for our compensation. From there, we have to find our Z, pitch, and yaw values. The easy way to do these we found is to just put them in a robotic spindle cell for polishing the load. And then Ryan's going to talk about our toolpath generation.
Now that we have the alignment of the lens, we need to determine the shape of the lens and we want to measure where the real lens sits in 3D space and probe for imperfections. To do this, we can use the formulas from the previous slides to determine the XYZ tilt angles for the nominal mirror that we're trying to create. The nested Looking at the left MATLAB code here, the nested for loops are used to move between equidistant points, like shown in the picture above. At each of these points, we use those formulas to get the nominal characteristics of the mirror and save them to a matrix. Once we have those points, we need to probe the surface of the lens to check for imperfections, so we know how much we need to polish off the surface. Looking at the MATLAB code on the right, this is used to actually code the probing process. Again, we use two nested loops to go from point to point, but at each of these points, we want to go through several steps to make sure that we get a good, accurate data from our probe. So for each, we want to move quickly to a point above where our probe point is with clearance so that we don't hit anything. We want to do that very quickly. And then we want to move down and get as close as we can to that nominal position that we want. And then from there, the next step would be to move very slowly, looking for those load cell readings. After that, we want to move away, creating more clearance before moving to the next point. At which point the MATLAB code just repeats and then goes until we don't have any more points left on the lens. Next slide. These are just plotted values for each of the joint positions over the toolpath for our X, Y, Z, and roll characteristics. Yeah.
Then once we have those values calculated in MATLAB, then we can perform a motion simulation with rendering. Unfortunately, several open source or freely available robotic simulation programs were unable to simulate this robot by virtue of it having separate prismatic and revolute joints that needed to cooperate. Many such software packages only allow serial robots rather than parallel or cooperative robots. So in this case, since we already had a CAD model that we were able to have in SolidWorks, we were instead able to perform a motion study in SolidWorks alongside the CAD design by importing each of the joint positions that were supplied by the MATLAB code and using those to control either linear or rotary motors to render that motion path in real time. So, Kevin, if you could discuss the probing further.
Okay, so this is our example of our load cell readings we got for our robot. They're just the readings that are separated into non-contact, contacting, and the in-between measurements. We then use these to perform linear regression on our former two portions. On the right is the general form squares linear regression equation. Regression is performed on contacting and non-contacting portions of a load cell. The intersection of these is where we find our height for our surface. And these values are repeated multiple times in order to find all the height distances along our load cell. The next slide is a picture of the errors, our measured and our nominal surfaces. Recall that the X center, Y center, and our roll angles were already compensated from our edge finding. And from there, we take these values to find our least squares best fit plane. The equation on the right is we got our equation and the matrices for our least squares fit plane. Since the XY probing points are symmetrical, the matrix becomes a diagonal matrix, simplifying these inverse calculations. We then obtain our pitch, yaw, and Z values, which are then used in the transformation matrix, like I said, for our machine tool pathing. So the equivalent angles are axis angles. The coefficients of these angles from the probing results are used to obtain our rotation angles and angles for rotation matrix along our tool paths. And these are just some of the equations and matrices we use to find it all.
now that we have our probing points and our geometry compensation, we need to generate a path for the polishing machine to follow. To do that, we first need to define some of the parameters that like travel distance between points and distance between each pass. For our application, we set it at 2.5 millimeters, but in actual real life scenario, this is a much smaller distance. One other major thing to note is that during each pass, we also want the tool to go past the edge of the lens so that we make sure that every bit of it is polished. Within our major parameters, we have defined here, it is also defined that we go about 10 millimeters past the lens on each pass. Next slide. This picture on the right is what the actual tool path generated looks like from our MATLAB code. The code shows a nested while loop, the big one setting the boundaries for when to stop when there's no more lens to be polished. The first nested while loop is meant to advance the tool in the positive X direction, moving it from left to right across the lens, stopping 10 millimeters past the edge. And then after that loop, we have a statement that moves us forward to the next pass in a positive Y direction. Then we have the last nested while loop does the same thing as the first one, but moves the tool in a negative X direction so that we go from left to right, forward, right to left, forward, and then so on until there's no more lens left to be polished.
So now that we have a series of nominal points on a perfect optic, if it was perfectly mounted, then we need to take into account the results from our geometry probing and use those transformation matrices to translate from a perfect substrate to the mirror as it is actually mounted in the machine. Then, now that we have those series of XYZ points and tilt angles, then we can take the normal vector perpendicular to the optic surface, move along that line by a distance equal to the length of the tool from the virtual pivot point on the machine. Then that gives us the XYZ position relative to the virtual pivot point. And then we can use the inverse kinematics shown previously to calculate the joint angles required for achieving that orientation. After we have that MATLAB code, then we can export each joint value as a separate comma-separated value file in SolidWorks, and concatenate that with time, import that in SolidWorks, and then we can simulate the raster toolpath shown previously. These are some plots of the joint displacements and velocities for each stage.
Sorry, I know we are out of time. I'm gonna try to quickly burn through the slides. So as we mentioned before, our initial plan was to use Robosim to simulate our robot, but then we realized that it cannot handle this kind of applications. So we had to do all our calculations using MATLAB and feed that into SolidWorks to simulate our robots. So please move to the next slide. Possible improvement would be using kinematic mounting, because as we saw in the video, we were depending on the vacuum truck, and in case we have a failure or a fault or a power outage, then this will cause problem, and most likely this will damage the lens or the mirror we are trying to polish. Next slide, please. So as we discussed in the past lectures, we insisted a lot that we discussed a lot the advantages of offline programming. So using the same techniques we use in this project, we can design the robots for different applications, such as welding, CNC, and coding. So questions, comments?
Great job, Group 16. All right. Well, I have to say, this looks like a ready-to-use application. Are you guys already polishing optics?
Well, unfortunately, our simulation experience during COVID was quite limited.
Okay, but it sure looks like that you guys are ready to actually build the machine and start polishing some eyeglasses, maybe at least. Okay, well, this has some serious math, and I have to say your group did probably use all of the math background I taught. So this is great. Anyway, let's open up for questions for group 16. Any questions for them? And guests can ask the questions too. Anybody can ask. I think everybody is still subdued with all the math you presented.
Apologies.
Yeah, a lot of math for sure. So, well, it's definitely a complex project you guys picked, right? So I think it's really a great way to think through this and apply the math needed and how to compensate those curves and all that stuff. I really think it's a great try, right, of, to implement this. So really, you should be proud of yourself. So there are real world applications actually on polishing, and we're currently doing, I think some of you probably love this Chevy Corvette. We actually do some exterior panel robotic polishing just to make sure that looks really shiny, really great, right? So if you ever got a chance to visit Bowling Green, and you probably want to look at that even on the road, it's beautiful. So I think what you guys do can really contribute to that. Offline programming is absolutely a must-have. So you guys are on the right path. Do appreciate your sharing, your experience and challenges. Thank you.
Thank you.
Great comments, Yanli. And I think what I liked is that since this is such a precise application for polishing optics, you're talking microns there, that the idea of probing to actually figure out how much polishing is needed in that area. So you're actually converting the probing force to how aggressively you're going to polish there. Is that how it's done?
Well, the probing is largely used for the geometric determination of the optic position in the machine. However, for precise optical corrections, there is auxiliary measurement that's performed on instruments such as touch probes, stylus, profilometers, and interferometers.
Okay. It's fairly complex. One more question I had is, this is, I think, the first example of a cooperative robot. This is not a single serial chain mechanism. You have one 3-degree of freedom arm, which is holding the lens, and you got a 2-degree of freedom polishing mechanism. Is that correct? Did I say it right?
Yes, it is.
Okay, and then you have a common tool in between. So it's a really, you can apply the cooperative robot methods we talked in the class to actually do this. Did you use those, or was that more or less you did the whole thing as a single kinematic analysis?
We, since the cooperative analysis was later on in the course, when we started this project, we had used some more brute force serial kinematics techniques.
Okay, well, you may want to redo and see if it helps you, make the whole analysis a little bit easier. All right, any other questions for group 16? Okay, well, the last suggestion I can give you can use super glue to hold the lens instead of suction.
Well, we need to be able to take it on and off to measure it.
Yeah, I'm just kidding. But that was good. Good job, group 16. Excellent demo and presentation.
Thank you.
All right, let's move on to next one. And we have a magnetic structure builder robot, group number 17. Take it away. Introduce yourself first and then share the screen, and then the demo and the presentation. Go ahead.
All right, well, hello, everyone. My name is Troy Conlon.
I'm Alec Hill.
Ivan Cortez.
And I'm Nate Dumitrescu. We'll be showing you our project on the magnetic structure building robot. And the basis of the project was to create a small structure using magnetic rods and spheres. Without further ado, here is our demo. All right. As you just saw, the application we focused on was to have a robot build a magnetic structure foundation. The purpose of this was to show proof that even larger scale buildings could be built by robots. As you can see in the top right image, some robots are already used to construct some structures, but we thought maybe one day robots could make even larger structures or even set up the foundations for homes or other large scale buildings. The robot we were using during our project was the X-Arm 6 DOF robot. Really, it's 5 DOF if you ask Professor Mirza, which we programmed to construct the structure using magnetic rods and spheres, like I stated previously. Hopefully in the near future, robots will be implemented in the construction field to make construction safer, faster, and much more relaxed on the construction workers themselves. The materials we used for our project included the X-Arm robot, a metal plate to help support the structure and keep supports from falling over or moving out of place, the magnetic toy kit, which we used as a foundation and building blocks of the structure, as well as a 3D printed gripper. Originally, the gripper pads that came with the X-Arm were very unreliable, dropping pieces and not really having a firm grip. So after a few tries and modifications, we're able to design a gripper for the X-arm that could get a very firm grip, very firm and reliable grip on the spheres, as well as the rods. You can see the modified gripper on the top right, as well as the other materials we used on the bottom of this slide. Now I'm going to be passing it over to Ivan, who will be talking more about the tool design and programming of the robot.
Hello, everyone. One of the multiple challenges that we encountered was how to grab, as Alec was saying. This robot is not ideal, right? So the force that applies in the tip itself is the material is not ideal for our application. So we decide to design our own tool. We use PLA material, a 3D printer, and we were thinking to actually do two tools, one to grab the rods and one to grab the spheres. But we decided to combine both, and the goal was like design a single tool that was able to grab regardless if it was a rod or a sphere. So we were successful on that. The program that we use to design the tool is one of the most powerful programs, is CATIA V6. I think in the industry is the most popular, and the other one is NX. I believe GM is using NX. This is very small piece. It's a symmetric piece, so meaning that we can use on the right hand side and the left hand side of the gripper. It took only 20 minutes to 3D print this piece, so it's pretty small. And we just reuse the same screws. Next slide, please, Alec. In terms of programming the X-arm, we use, as other team members already said, this X-arm robot has 4 different types of programming, but we find that the PC interface is way simpler. So we just position the robot by hand on a very close location. And after that, we input those values to the servo. So we fine-tuned using those values. And with that, I will pass over to Troy, who is going to explain more about the workspace that we use and the metal plate.
So after we established, the workspace that we'd be using, we positioned the robot so it was directly over the metal plate. That's way the metal plate could assist us in placing and picking up our pieces because they would snap on and off. Then it was just a question of, what are the limits that the robot can reach? And we found that it could pretty much pick up and place a piece anywhere on our metal plate. The only real servo that was an issue was just the base rotational servo. So there was just that one dead zone pretty much toward the back. So from that, we were able to calculate how many pieces we could put on either side and, to make sure that there was enough clearance. So as the arm went down and opened and closed, it wouldn't knock any other pieces while it was doing so. So we could probably get about 15 pieces on each side. And then we wanted to have a good established ending zone. And so then we had it smack dab in the center. All right, next slide. So from there, it was about, determining, well, what sort of structure can we make? Unfortunately, the X-arm is very limited in terms of its degrees of freedom. So with that in mind, we had to, we couldn't make some crazy huge structure. So from those previous calculations, we have about 30 pieces that we could work with. So as long as it was smaller than that, we were fine. And then the design would be as follows. It would place the base blue poles first. Then it would drop in these horizontal pieces, and then the next level, and the next level, and the next level. With that in mind, we had to make sure that the arm was capable of even placing these pieces, because there's issues otherwise. Okay, next slide. So we wanted to start simple and work our way up, and unfortunately, we weren't able to work up that far. The X-arm has a lot of limitations that we ran into, the worst being that the wrist wasn't rotating as freely as we thought it would. It was only around like 80 or so degrees of freedom, so we couldn't actually rotate a piece like from 90 degrees to 180 degrees. And from someone else's presentation, it looks like it actually can. So there might just be an issue with the servo that we had installed. So that's another conversation. But otherwise, our design had to change as these limitations became more prevalent. The fixtures that we had for the horizontal pieces that we used to pick up in place, the arm wasn't able to open wide enough to grab those two. So then we had to sacrifice those horizontal pieces as well. We wanted to do some crazier stuff, like we ended up dropping some pieces from the sky, and ironically 3 out of 3 times it worked, but something about that just seemed off, so we scrapped that idea too. But otherwise, you know, even with the unreliability issues, we were still able to make this structure fairly consistently, and thus we were able to say that, you know, I think we'll be okay. And even with the slow movement, there wasn't a whole lot of control we had over the movement. It was pretty much that. It was able to fit the time of the demo video quite nicely. And with that, I will hand it over for Alec for the wrap up.
Nathan.
Yeah. So, so given the goals of this
Nathan.
given the goals of this project, our project was considered successful because we did achieve the concepts we were trying. Obviously, with an actual industrial robot, much more elaborate and advanced structures would be able to be built, as I mean, we've mentioned and other groups have mentioned. The X-arm wasn't as robust and accurate as we would have expected, but it was still fairly easy to program and use. One of the things that we found while we were starting to work with the pieces was that because of the magnetic nature of the pieces, it helped to snap them into place. But the shape and the size of them did limit how elaborate we could build the structure, and it caused limitations with the tooling that we made. Next slide. So some potential next steps, if we had some more time, would be redesigning the tooling to help just handle those pieces better. We also could have moved forward to programming it with Python, just to help with like speed control of the movements. Another idea that we had was integrating like an automated tilt table to assist with any of those angles that we were having trouble hitting. Or we could have possibly integrated another X-arm to help with the building of the structure. Or we could have transitioned to a higher grade robot, like a more expensive desk robot or an industrial robot. Next slide. All right, thank you for listening to our presentation, and thank you for the guests, to the guests for attending. If you guys have any questions.
Good job, group 17. Good demo, good presentation. All right. So I was really hoping that at the end that you push those sticks to form a roof, like a pyramid roof. Yeah. Anyway, so let's open up for a question for group number 17. Any questions for them?
Yeah, hey, Kel, this is Mike. Has the group thought about, they talked about doing construction and applying it to the construction industry. Are they referencing mostly to look to the prefab, or have they thought about the challenges facing it to do construction in the field?
That's a good question, Mike.
I would say more or less construction in the field, as it'd have to, like, I guess, be transported to the work site and then put up the foundations, like I said, or put up whatever they needed it to put up.
Okay, with the follow-up to that, if I'm doing a prefab in a building and making prefab, I have a controlled environment. If I am taking it to a job site, I have changing environment, changing power requirements, and changing foundations. All soil's not the same throughout the US. What have you put thoughts into addressing those type of issues?
We have honestly not really addressed that, but with your prefab question, it could also apply there. I really didn't expand on that either, but like you could bring it into an existing building with a controlled environment and it'd be able to build pretty much whatever you needed to build, like maybe a desk, a table, a counter, a kitchen, a whole kitchen, put together a whole kitchen, move the refrigerator for you. But
yeah, so this project can be combined with the IKEA group, and you can make house-size furniture. So what Mike is saying that in a control environment, you could have a nice robot setup, which can get the parts from a definite area and just puts it together very quickly, and modular sections can go away. So that could be a good way to do it. Large structures there to build there. But the other thing is that on site, have you guys seen those robots which actually dispense cement to do like 3D print walls of a house? Did you guys ever see those? Go check it out. So there are robots which, and I think maybe it's KUKA. Mike, is that a KUKA robot which does it? Do they have
It is a KUKA robot.
Okay, so go check out those videos. So it's like a huge robotic 3D printer, which is using actually cement to make walls. It just puts us just like a glue, but thick cement, and it just goes around and builds up a whole wall. So there are many different methods, and you can see that there is a lot of interest in the construction industry to automate a lot of these things using robots or other large 3D printing mechanisms. All right, any other questions for group 17? So I have to say that one of the things you guys did was you ran into use of proper tools to handle part. That's so important and so essential for any application, that you have the right tool at the end of the robot gripper to perform it. And what you guys did was that use a single tool to handle two parts. And that's also very important. If you can do that, you save a lot of time to make any tool changes for the robots can have tool changes also, or they can switch to a different tool which is on it. You can have a automated tool there, but having a single tool handling multiple parts is a good way. Reliably picking up is a good way to make the application perform much quicker. So that was good. And for the work envelope, most of the time when you do robotic applications, you actually design them offline, so that you can move things around to say which is the ideal location for parts and where the assembly is going to happen. It's much easier in an offline 3D simulation. And then when you have everything just right, then you build up the robotic cell. So that's also how industry uses. So it was a good thing that you were thinking on the right path, that where should we place the parts? Where is my work area? What areas the robot cannot reach? So all that is very important.
Just as a final comment, Professor, the first comment that you made about the pyramid, we really tried to do that actually, but the issue, we spent several hours trying to at least to capture one shot, but the issue is when we are moving the rod a little bit like not vertical, it spins on the ball itself, so it's pretty difficult to do 4 of them.
Well, I was still hoping that you would be to put a ball at the top and then make a pyramid house, or at least that that guy was able, you were able to switch on at the very end, and he wouldn't be able to turn it off.
Yeah.
Anyway, great job. Any last questions before we move on? Okay, in that case, I'm sorry, go ahead.
Yeah, I was just going to really compliment you guys. I think it's a very good thought to try to use a robot to replace those, kind of like a workers, right? A lot of times it's not only safety, it's ergonomics, it's all the things related to them, right? I think you guys really come to say, let me help those building workers, right? And to make the work. I think the professor also commented on really trying to combo the tools, one to do more things. I really like that. I think it's a great idea because a lot of times, right, you have a more universal tool. You can handle the work. It's certainly it's a cycle time advantage. It is also a lot of other things you avoid to do. It's certainly also cheaper, right? So I think for real world, I would say application, those are all really good considerations.
Thank you, Yanli. And yeah, I will second all of that, that these are very important things. And the only way to learn is to actually do application, and then you figure out those things. So I'm very happy that most of you are actually, by doing these applications practically, either in simulation, designing your application, or in reality, you guys are learning the very important stuff for robotic applications. Great. Okay, great job, group 17. And we're going to move on to our last two groups. So group number 18 is, oh, we're going for a robot ride. So please introduce yourself first and then share your screen with your demo and presentation. Go ahead.
Hi, this is Naveen Kumar.
This is Tyler Kavanaugh.
Kayla Kolominsky.
This is Zichuan Liu.
So ours is a fun application. Hope you enjoy it.
Our ride was made to demonstrate the flexibility and the range of movement of the KUKA robot. Some applications that we thought this could be used for is obviously entertainment of a coaster, which we presented in our simulation. We also thought by applying VR or AR, you could do gaming. So you could have the coaster represent the video game you're playing. It could also be used as a simulation tool for places like NASA to train their astronauts for different space simulations. And I've also seen a similar robot used in medical for chiropractic and things like that to test people's eyesight and how they react to different movements. Next slide, please. Here we have a short video of the actual KUKA coaster, which is from their website, just in case none of you have seen this represented before. For our tool, we had to design a seat. I designed it personally in CATIA just because it was a software that I was already familiar with, but SolidWorks and other things would have worked with the simulation tool we were using. I modeled it to represent like the average roller coaster seat that are used on real roller coasters. And we did run into one issue, as you can see on the bottom of the design from CATIA. I designed it with the frame at the bottom of it. So when we imported it into RoboDK, it aligned itself on the KUKA robot, as you can see in the bottom left image. And it was easily solved by changing the X, Y, and Z parameters of it in RoboDK. Next, we have Tyler talking about our simulation tool.
Like Kayla mentioned, we chose RoboDK as our simulation. The reason we did this is, one, it's very user-friendly. Basically, we found a really good startup guide that RoboDK provides that taught us quickly how to use it. It also was very valuable into using CATIA, as well as coding in the Python for choosing what level ride you wanted to go on. So it was very helpful. Next slide. So when we were creating the simulation, we ultimately chose to use the KUKA KR1000 L750 Titan. Due to its long reach, it basically can span out to roughly 12 feet. It's a 6-axis robot. It has a very big payload, so that's also good. And basically the range and motion speed is very good, especially when you're going on the fast setting and the robot is going very quickly. Next, we had to make multiple reference frames within RoboDK. With all these multiple reference frames, we basically had to take those frames and make them into targets for the KUKA robot to just follow along the path until it reached the home position again. Next slide. And here is the Python snippet that we used, which basically allows the user the 3 different intensity levels, as well as the 3 different trajectory levels as well. So basically, as soon as you start up the simulation, you can just choose one or the other, and it just basically starts from there. Next, I'm going to send it off to Zichuan to talk more about changing speeds.
Yeah, there are 2 speed settings, the linear speed and the joint speed. In this project, all the speed are set as joint speed because there is a lot of constraint on the linear speed, and it is easy to meet the singularity problems. Set the speed before the robot moves. The robot speed will follow the speed setting when the robot begins to move. Next one. So there are three types of ride. The first one is the experience version. The trajectory is put in the slide. Because this is used for the tourists to experience, so the speed is not very fast, and the path is short, more like sightseeing. The fastest joint speed is 5 degrees per second, and the joint acceleration is 5 degrees per second squared. In our vision, it can be combined with the VR goggles, so the tourists can take the virtual tour in a small place. The second one has more complicated trajectory and faster velocities and accelerations. The fastest joint speed is 30 degrees per second, and the joint acceleration is 6 degrees per second squared. In this mode, tourists can feel experience like a roller coaster being tossed around. In our vision, it also can be combined with the VR goggles to experience immersive space combat scenes because it is more intense. The third one has the same trajectory as the second one, but the speed and the acceleration are faster. The fastest joint speed is 50 degrees per second, and the joint acceleration is 10 degrees per second squared. This one is for the tourists who want to challenge themselves. If they want to play something crazy, try this one. So next one, we'll send Nami to talk about the simulation.
Yes, along with the ride itself, we also wanted to make the ride free for users to just try it out. I mean, no need for another person for you to select. So in real world, it would be kind of a touch screen interface where user can select a ride, and it can, he can just ride as much as he wants, and he can let go. And in the end of the ride, we wanted to provide a message to the user. It could be anything. I thought of also adding, like, collecting feedback from the user, how was the ride, kind of thing. So for the programming part, there were two parts. One for moving the robot itself, which we did using the RoboDK, and the instructions were pretty simple. Like here you can see the instruction for moving a joint to a target and setting a speed, and those programs can then be converted to converted for offline programming. Basically, we can flash the same code on the real robot. And another part of the programming was Python scripts, which are not shown here. That was just simple Python scripts to get the user input, and based on the user input, it would select accordingly a program to run on the robot. So in conclusion, the project was success. We were able to show that robots are really great for entertainment industry, and this is just tip of iceberg. There are limitless possibilities for these kind of applications, like VR rides and gaming. And even if we put two of these robots on rails, we can even play laser tag with these, I guess.
Good job, group 18. Good presentation, good demo. Anyway, so by the way, reminding everyone that I've already sent the link where on the YouTube where all these demo videos are there. So go and watch there in full glory. I know it doesn't, the sound and the video becomes choppy on the Zoom session. So if you really want to enjoy all these videos, which all the students made, they are really, some of them are, most of them are really good and funny and everything. So I really enjoyed watching all of those videos, very creative. I did become dizzy watching this video though. Okay, so let's open up for questions for group 18.
I have a question. This is Don from CCS. I loved all three projects so far, but when you mentioned entertainment arts, did you guys think about like any kind of themes for the robot in terms of like just kind of a character that you guys would develop for it? Because I think it's really, I could see that kind of robot like microbreweries popping up all over where you just have that. And I could see kids in lines choosing what level and having a really interesting theme. Did you guys talk about that at all in terms of a theme or a character?
Great question, Don. Well, good.
For our project specifically, it wasn't mentioned of a theme or a character. We did choose to color it. Tyler chose the colors red and blue, but the back of it ended up showing yellow on RoboDK. So I personally thought those colors together reminded me of like a superhero kind of theme, but we never really discussed it.
I think it was pretty cool. I think it's the size of it seems like you could put it in different places, because we think about those kind of rides in a big amusement park, but putting them in places where in smaller venues that would be more accessible to a wide range of people and certainly kids. It was great. I really enjoyed that. Great job.
Yeah. And in microbreweries, I mean, after a couple of beers, you don't even need a robot for that experience.
It is certainly some kind of a thrill drive, right? People can experience. So just a thought, a question. So what kind of safety considerations when you do this kind of thing, right? Also, how do you try to accommodate different size of people also for this kind of entertainment, right? Adults or little kids, things like that. Any thoughts when you guys design it to put into those two perspectives?
Excellent question, Yanli.
At least for the size wise, I would think the seat size should accommodate most people, and the payload we selected was good enough for any kind of person.
I also think for the seat, you could add adjustable straps within it so you can tighten them for children so they don't have a chance of falling out.
And during the project, there was also a point we wanted to add a kill switch. So if someone panics, he can press that and the robot stops and comes safely to a stop. But it was really hard to imagine when someone is panicking, what he will press and where to place that such a thing.
Yeah, so that's a very interesting consideration, right? I know for robots, a lot of times people call it deadman. When people panic, you don't really push the button. You actually maybe somehow unconscious, kind of like unintentionally just release it or something, right? So when you don't make it the way it's supposed to be, then it stops. So
a vision solution could be one thing.
But either way, safety probably is something, I would recommend the team to consider as at least give it a really serious consideration when we apply those kind of applications in the future.
These are excellent points. If you guys remember from the lecture when we were talking about safety priority, when you're doing robot application, in your application here, your tool is the seat and the part is the human. And in our safety priority, we said the first thing you can sacrifice is the part because you have so many of the parts. Can't do that in this application. The highest safety priority is the part, the human itself. So how do you make sure that the robot is not gonna smash the seat into something, all that? And I don't know if Mike is still here. KUKA has a robo coaster, which they have it in Legolands, and the snippet of video which you showed. Maybe Mike can talk about, what took to make that robot safe for a human to ride it.
Okay, thank you.
Not only that, right? Additionally, you would want to think about what if we power out when people are playing with this? You also need to make sure they're still safe, right?
Absolutely. Yeah. Mike, you want to share?
Sure, I'd be glad to. Well, I'll address her previous question. Yeah, if you lose power, basically the robot stops, but there is a mechanical way, joint by joint, to get the operators back to a platform, or it can be done electronically. So that has been taken into account. One of the things you have to do when you start interacting with humans, whether it's in amusement or medical or whatever, you have to look at the forces the robot can generate on the human. Part, we don't care. It's going to break or not break or get crushed. A human, we have to look at the G forces being applied to the human. So that's one of the key factors you have to take into consideration when using a robot in an application such as this. The other major factor you have to do is you have to look at the failure points of the robot. We talk about if something fails on the robot in industry, it's not usually a big issue if you do your risk assessment. If you're carrying humans, then it may be an issue. One of the extra functions that happen when doing a ride like this is metallurgical tests via X-ray or ultrasound has to be conducted on the robot on a periodic basis to ensure the mechanical structure integrity that you can't see. You don't know if the molecules in the casting are failing or whatever from stress. And there's microscopic stress fatigue in the casting. Things of that nature you have to do when you're working with humans, where you wouldn't have to do that working on an industry robot. And then lastly, I put in the chat, but they talked about in their presentation, they said, yeah, why don't you take and put the robot on the rail? And that's the concept behind the Harry Potter ride. They basically took the roller coaster and put it on a rail, and it moves along on a track, interacting with other animated simulated situations. So yeah, there are many applications. They've hit on a lot of key ones where you can expand it using, virtual reality goggles, even a cinema screen in front of it so the person can feel that they're going through. There are many different applications. They've hit on quite a few applications where they could use this. I mean, it's just, like you said, it's an artistic, think of it as an artistic tool. How could you use it to provide enjoyment to a person, to give them entertainment? So yeah, it's, but the safety has to be taken into consideration. And wherever you use the robot, you still have to, think about safety, whether it's this, whether it's at a factory, or whether it's at a trade show. It all comes into play when you're thinking about robotics.
Thank you, Mike. That was an excellent, detailed analysis for the entertainment side of robotics. Wherever you have humans within the workspace, you have to take into account many other considerations if the humans are on the robot itself. So so hopefully that gives you an idea, whenever you are designing robot application, there's a risk analysis you have to do, and what is highest on that risk, safety priority depends on what kind of application you're doing. Now, you guys did mention that you saw that there was a medical use for this, for eyesight testing. You want to say that again?
I did it. I happened to experience it in a weird circumstance. My boyfriend's going into chiropractic, and I toured some grad schools with him, and they had a very small one similar to this. I don't know what robot, but I took notice of it because I'm in this class right now, and they use it. So they have, it's like in a circular cage. They put someone on it, and they move them around really fast, and then they'll stop them, and they have to focus on a picture. They have tons of pictures all around, different memes and stuff, and they're like, look at this one, and they have a camera very close to this person's face, and they'll see how long it'll take the person to adjust once it stops or while it's moving, to get them to focus on the different pictures. And somehow they use that to adjust, and they can see that your brain's lagging, because if it takes your eyes too long to focus on something, it means that something in your brain is messed up, and your brain is filling in moments that you're not actually seeing, and they treat people based on that. I sadly don't know the medical behind it, but
no, that is very interesting. This is all kinds of interesting stuff. And you can see that, you can come up with new applications for robots to actually help out in all these areas. Any last questions for group number 18? Now, I did notice that most of the time Ryder spent upside down. Was that on purpose?
Yeah, actually, I just want to show the freedom of the robot and the flexible of the robot, because I'm the designer, like how they move. First of all, I want to use the path in the video we have shown before, the KUKA, the robot video. But I think it's really hard, because they have lots of rounds to move separately. So I just design by myself. So I think it is funny, but I would not take the ride actually. When I finish it, I told myself, if I take this one, I will really mess up in my brain when when it's finished. So I just want to show how it can upside down and move different direction. So
no, it was pretty good. It was pretty
Yeah.
good, and I think the rides I've seen in Legoland and all, it was pretty similar looking motion. So that actually worked. The people enjoy those rides, and there's long lines to go on those rides. So good job, group 18. And now we have finally the last group, and I do have to mention this group started with 4 members, but unfortunately by the time we reach the final project, only 2 are left. So they get special, we will give them special treatment, right? Okay, so this last group is gonna present Lockbox Robot. So introduce yourself and show us your demo and the presentation. Take it away.
All right, hi, I'm Adam Islak, and I'm one of the group members of Lockbox Robot.
Oh, hello, yes. Hello.
Hello, I can see you, please.
Okay, okay, so you can introduce first.
You want to introduce yourself?
Yeah, for me?
Yeah.
Yes.
Yes, this is Tianjun. So I'm introduced for the project. Okay.
So we worked on the Lockbox Robot. Short introduction before we go into the demo video. Our goal was to create a robot application that combined both the X-arm and an Arduino. So we wanted something that, I guess to describe it, could be used with an external controller. That was our main process, and we wanted to do something where we combined our previous knowledge in other classes into this class.
Okay.
playing again. Yeah, so that's our short little demo on our robot. As you can see, we set it up so it picks up the key. I punch in a code on the keypad, and then it picks up the objects that I told it to do. But onto the slide here, the project process. So our first thought was actually to do like a dice throwing robot, because I have some dice and I'm like, oh, that'd be fun. See if I can get it to throw, simple numbers, see if I can get something specific, or even like stacked dice. If you've ever seen people, they like switch the cups around. I don't know how they do that. And then the second application idea was something that could fold laundry using like those fancy like t-shirt folding things, because we wanted to do something practical.
So yeah, for this project, so we built the lockbox with user robots. So when people enter the certain passcode on the keypad that attached to the Arduino, Arduino will send signal to the robot through the serial communication, and the robot will take the action to store or retrieving the item to or from a different storage location.
So here's like the base level Arduino design overview of our project. So on the left, we have our simple Arduino circuit where we connected the membrane keyboard that comes in that fun kit that we all have, that uses this that we use it through 7 pins. And then additionally, to connect it to the robotic controller as shown in the middle, we used the RX and TX pins because that's the native support for the robot controller, in addition to a ground. Not powered, because as I learned the hard way, if you connect power, it gives off 5 volts, and I thought it was taking 5 volts. So I may have sent 5 volts going into each other. Here, I'll do this one, Tijan, you do the next one, sorry. This one, so on the left, you can see that this is like the WeMake software. This is what the company that creates the robot actually recommends to use in a secondary, in like a peripheral programming type of way. And it goes with the Arduino. So it's just drag and drop type coding, but it wasn't super useful for us because what we were creating was something different than what their like presets are. They have all these fancy preset things where they set it up with an ultrasonic sensor and it can see if something's in front of it. I thought that was pretty cool. But we mostly wrote our code using the Arduino IDE. The snippet of our Arduino code shown is like the base snippet for the XR moving. So the key action that we call in the Arduino code is the run action group. And this tells it it says, hey, this is what you need to do. This is the motions that you need to do. As we'll explain later, we program the motions using the, I don't know, I can't remember what the program is called for the robot, sorry. But the robot comes with the program as the other groups have shown you, and we can download those action groups onto the robotic controller. And then when we call them through the Arduino, it performs them.
Yeah, so on the left one, we just use different cases, and and those are run action group is that means run action group 0 and 1 time. So when you enter different passcodes, you will enable the different group we stored in the robot, and will take the different action. And the right is the code for the password, and we can set 3. We just set 3 different passcode, and you will Arduino will verify if it matched the what we entered, if it matched the code we stored in the Arduino.
So moving on past the Arduino, this is the XARM software that I was talking about earlier. This is just the post in front of you is just the basic user interface of it. Here you can see in that top portion us writing the action groups. And so each of these action groups, we either trained it using the ability to train it by moving it, or we trained it just by changing the values in there. And so once we created those, say we created action group 1. So as you saw picking up the cylinder, that would be action group 1. So I punch in the code would say, okay, this is the code for action group 1. The Arduino would send action group 1, and then the robot arm would perform it. So with the results, I mean, as you saw, it works. I like it. I think I love it. You know what? I need to be confident in my project. I love this robot. It picks up the things in kind of like a set. It can pick it up in a set trained motion, and it obviously can't see, which is one thing I don't like. So problems encountered. The Arduino and the writing of the code for it was actually one of the bigger problems that we had, because there is not a lot of information. Like I spent hours looking through different user manuals, trying to find something that could help me. And they have, you know, these nice videos online, but they're all for their own kit, you know, and it's like, oh, buy our Arduino kit. And I'm like, no, I know I can do this with mine. But eventually I figured out that it was a library. I had to download an extra library to the Arduino, and that was the missing key for me. And then we actually had some problems connecting the robotic controller to our computer. I don't know if it was my computer or something, but like it did not want to recognize it for a while. So that was kind of a minor setback to us. And then third, I forgot to mention on the slides, is that if you notice in the video, the arm is a little shaky. It really kind of struggled. It struggled holding the objects, and that was partially due to the speed that we were having the arm run at, and then like the angle that we were using the arm with. And so like in the future, we would try to improve that.
So how can we, how would we expand? So, so we will be interested in implementing a program or bigger robots if we took the into the how can I say that? So bring it in the life, and we can and the system you can the robot system you can see is not really static, and it will shake in the tape. And also I want to say is we also can add a screen on the Arduino, so it can show what the type what you type on the password is. And also it will give a notice if we enter the wrong password. So and for another thing is the security. If we really bring it in life, we need some like security stuff to increase the security system, like to give a longer password, or we can enter the password by ourselves. That's it.
Yeah, so and then we'd like to expand to actually so it picks up a lockbox and does the job.
Mm-hmm.
That would be a lot of fun.
Mm-hmm.
But yeah, there's our robot. Sorry, it's kind of a brief presentation. There's just two of us. We tried our best.
Awesome job, group number 19. You did a good presentation, good demo. Good job. So you obviously had a lot of fun doing this project, and that's what counts, really. If you're having fun, you will be learning a whole lot. You know, even, you know, little things, trying to overcome them. That's the whole idea of this hands-on project, is to try something and make it work. And it's the biggest pleasure is at the end, it's working. You know, that's the biggest payback for doing these projects. But I could see that at the end you had a Thor robot with its hammer hammering away on your laptop.
he did not like that the marker box, and he struggled there. You know, he had to warm up a little bit, get a little stretch in, and he couldn't find that cylinder. I don't.
Well, you know, this robot has its limitation. The servos are small. It can only handle very small objects and weight. But you guys did a good job there. All right, let's open up for questions for group number 19.
So you got my attention on folding the t-shirts or the shirts.
Yeah.
Talk a little bit more. I'd tell you what, I'd buy one right now. So tell me about that idea. Is that something that you would like to would want to develop more?
Yeah, honestly, like, but it was ultimately it was kind of hard with the way the arm was set up because it couldn't reach far enough, you know, to get to the end of like the t-shirt, like those cardboard pullers.
Right.
Yeah, because I would have loved for it to just, you know, pick from the laundry basket, put it on there,
yeah,
pull it up for you.
Well, I think when I saw that, I saw it got my attention. So I know, even if it needs more work, I thought that was a great idea. So
yeah, thank you.
Good job, you guys.
Yeah, we wanted to do something practical, I guess.
Yeah, I'm all about that. Practical robots, man.
Well, you guys.
I think you got a lot of customers.
Go ahead, Yanli. Go ahead. Sorry, go ahead.
No, I'm sorry. I was just going to say, I think the idea is awesome, right? And there are plenty customers want to have that kind of robot to help them with housework.
Yeah.
So it's absolutely, I would say it's an awesome idea. I also noticed one thing, you know, I do want to comment on it, is the communication issue, right? I mean, it's amazing we're all working more on, you know, robotics and others as we're in the smart world now, right? Every device is smart. Communication become so much more important no matter what we do. And you will be amazed how much communication error we do get in real world.
Yeah.
And I always joke about it. I say, hey, the plant have issues. If you look at it on the list, other than, you know, I would say conveyance issues, you know, kind of like a line stops, you know. If you look on there on the top pole, there's next one would be communication.
Yeah, for sure.
Yeah, networks down and robots or other machines will not move, right? And those really interesting, even with this, you know, kind of like a smaller scope project, you experience that.
Yeah.
I think that's really, I would say, a good indicator, right? In the future, when we design the system, we really also want to make sure we have robust network as well. I like the way, you know, Tianjin said, also cybersecurity, right? One security. And with robust, long password, you know, all that stuff. That's also another very important aspect when we put those automation anywhere.
These are excellent points, Yanli. And you guys actually interfaced an Arduino as an external cell controller for your robot. So this is something, you know, in the industry, you have PLC and a robot, and they communicate, and they use a standard communication scheme. So what Yanli is mentioning, that those things are extremely important when you're doing a cell design, where you have multiple robots, multiple PLCs, and other automation equipment talking to each other. They all have to know who are they talking to, and they are using the same communication scheme. So your serial communication between Arduino and your X-arm robot is a good step towards that, to understand, you know, how, and that's where you face the most problems. So that's itself is a hard task right there. Excellent point. Any other questions for group 19?
I have just a general comment, you know, picking up on communication. This is about the presentations themselves. You know, I come from the creative side, as you know, this is not about the engineering. But conveying a good idea with a good presentation is really, really important. And I noticed, for instance, in this presentation, you had a soundtrack behind the movie, which really helped move the movie along. And then some of the presentations, was either silent, and I don't know if it was technical problems or, the focus on the work itself. I know that on the project itself, but adding narration, adding good cuts within the video, and having beautiful visuals helps to communicate a good idea. And all of you had great ideas, and a lot of them will be enhanced, just by the way they're presented. So, communications, plays a part in talking to the robots, in programming the robots, but also in communicating that idea and what you're doing, to humans, to people like us. So I just wanted to mention that. But kudos.
Those are excellent points, Sam. And I think I may have touched upon it in my lectures, but maybe I should have a topic at the end about how to do good presentations and good video. It is extremely important, guys. When you go out in your careers, you can have the best idea. A poor presentation will destroy it. You will not be able to make others understand what's in your head. So it's extremely important that you have effective. You capture the attention of your audience, and then you deliver it in a very good way. And all these multimedia stuff helps. It really helps if you use it correctly. So what Sam is suggesting is that we need to concentrate more on the soft skills, even for engineers, because you're going to be using it all your life. So it's very important.
But I know these projects are short-term projects. They're what, 3-week projects. I know the focus is on the ideas themselves, and I do appreciate that. But just a little extra care would make them go a long way. That's all.
No, absolutely. Any other last comments from anyone? Again, these videos are available at the link. I will share the link with everyone again. And when you see it on YouTube, they are pretty good. I mean, on Zoom, because of technical difficulties, sometimes the sound is I like to watch movies in surround sound, and I really enjoy it. And when you watch these videos on YouTube with full sound, they are pretty good. So most of the students did a great job, but there's always room for improvement, right? And think of the ways you can deliver what you're trying to say in a very effective way, which is an excellent skill. All right. Any other last comments from anyone? This is open for everyone. And I know everybody did a great job. I really enjoyed all these projects. One big hand to everyone.
Khaled, I just wanted to say a shout out to Group 19 that they're the team that experienced real world challenges, because in the real world, they hit it on it. You have a team designed to do a project with a deadline, and you lose a team member for a variety of reasons, whether it's for personal reasons, whether there's a different project that they get transferred to, and all of a sudden you're down a team member or 2 team members, but you still have a customer with a deadline to complete a project. So in their college career, they really experienced what they could experience in the real world, and that's a tough thing to teach. So whether they realized it or not, they actually learned something very valuable in their project.
That was a great point, Mike. Yes, absolutely.
Agreed.
All right.
Professor?
Yes, go ahead.
You mentioned about teaching about like giving presentations and stuff, and like how to make good videos and stuff. I do suggest that, because I also have a minor in cinema studies that I completed. And I have to say, between engineering and cinema studies, I never learned like this stuff for presentations and like how to make a good video or to do any of that stuff. So if someone could teach it, that would be great.
That's Kayla, that's an excellent point. We could put together a good list of tips. I tried to give you for a presentation a set of tips how to do good presentation, but that's just for a presentation. For video, it's a whole, I mean, I'm not the expert, but we can go to some of the experts. If you're making a short under 5-minute video for showing off an application, what's a good way? You know, how would you construct the video, and what tools can you use? Again, you know, if you have sophisticated tools and sound effects and video effects, you can make a snazzy video. But what if with a minimal setup, what is the best way? So I like your point that maybe we could put together something to give to the students before the project starts, so they can use that to kind of do it. I like that idea. Noted. Any other last comments? Well, I want to thank you everyone again for your great job in doing the final project. I hope you all enjoyed it, this journey. That was the whole point, is, you know, learn in a fun way, very practical things which I cannot teach in class. You have to do it hands-on, try it out, and face some challenges and try to figure out is the best way to learn some of those things. But your theory, your background, which we hopefully learned in the class, helped you to overcome some of those challenges. Anyway, and again, thank you very much to all the guests who joined. And this presentation itself and all the videos will be posted on YouTube, and I will share the link, and share it with your friends, and be ready for the virtual expo, which is coming in a week, I think. So make sure to give your posters to Laura, and I will give them they already have the video links. So your videos and posters will be available on LinkedIn Virtual Expo. And thank you again. Great job. Now enjoy and prepare for the final, which is coming up next week. Bye, everyone. Thank you.
Bye. Take care.
Thank you, Professor.
Thank you. Have a great night, guys.
Thank you, Professor. Good night.
Good night.